Again, good morning or good afternoon. It looks like we have a critical mass of folks here in attendance. Welcome to the AASHTOWare Pavement ME Design webinar series. This is webinar number 3 in this series. Title of this webinar is the local calibration of the AASHTOWare Pavement ME Design program with the CAT, or the Calibration Assistance Tool. Today, my name is Ben Said. I'm the Associate Product Manager for AASHTOWare. I'm filling in for Hariner from VDOT as the moderator today. John Donahue with ARA will be presenting on the Calibration Assistance Tool today. We are recording this webinar, and all of the recordings are available after the webinar is completed at our new website, which is AASHTOWarePavementME.org. Membership hasn't changed since the last webinar. You can see the different members and managers from AASHTO. Just some quick housekeeping. Please keep yourself on mute. The Zoom features won't actually allow you to unmute. If you do have a question that you'd like to ask and you'd like to raise your hand, it is possible for me to unmute you towards the end, but please keep questions, unmuted questions, towards the end of the webinar. If you do have questions and you'd like to ask questions along the way, if you navigate to either the top or bottom of your screen, there should be a box that says Q&A. Please feel free to type your questions into that box. And you could receive either a written response back from one of the panelists, or if you don't receive a response back, we'll go through, providing there's time at the end of the webinar, a question if it was unanswered. We'll of course get to any of those questions as they come in. Before we get going and hear from John on the Calibration Assistance Tool, I'm going to launch a poll here, and I'll give everyone a couple of minutes to answer those questions, and we'll go from there. All right, thank you so much for answering the poll. We've got almost everybody answered here at this time. So I'm going to end the poll, and then John, take it away.
Okay, thanks, Ben. First of all, I'll talk a little bit about what the expectations are from people that are attending this webinar. Should have some basic working knowledge of running the Pavement ME Design software, either on the desktop or the web application version. And calibration preparation, I'll try to be careful about this. I don't expect you to have gone through a full calibration process, but at least start to, I guess, understand what it takes to initiate that. Knowing what pavement design types your agency is interested in verifying and calibrating the performance models for. Having some idea of where, what test sections you can select, whether or not from the LTPP program or from pavement management system sections within your agency's jurisdiction. Also, what the performance or the design threshold criteria is for your pavements, and how to go about doing the basic data collection for that. So I'm not dissuading anybody that maybe hasn't gotten into that yet, but just it's kind of good to have initiated to some extent that thinking about those things. Now, the learning outcomes here, one, you should have an idea. We'll go through, or we'll at least list all the Pavement ME Design models that can be verified and calibrated in the CAT. And we'll tell you which files or what type of files needed to be uploaded into the CAT for analysis. To some degree, explain how changing the coefficients, decreasing, increasing the coefficients affects the pavement design models, in particular the effect on damage as it relates to the distress accumulation. And look at the model fit statistics, or the analysis of variance statistics that are generated by the CAT give you some tools for critiquing those. And finally, and this is pretty important, defining what the responsibilities of the user are. There are definitely points in the CAD is doing the heavy lifting for you as far as the analysis goes, but there's still a lot of decisions to make at certain points within the process. So the user is heavily engaged all the time. So what we'll go over is an introduction. Not going to go into the pavement MED design concepts too much, but just a really cursory cover of kind of how the mechanistic models work as far as they relate to the damage accumulation transfer functions for the performance models, and discuss the type of CAD input files, what format they're supposed to use, the performance models that you can select within the CAD for verification and calibration, the performance data, looking at the suitability of the data that you have at hand and how they're going to fit into the experimental matrix, the verification process, which is always the first thing you do. You're verifying whether or not the global models or whatever your current performance models are, whether or not they still satisfactorily predict the outcome as compared to your measured data. And if they don't, then the next step is going to be calibrating and hopefully validating the performance models after you optimize the coefficients. And we'll have a little time for Q&A at the end. So first, the introduction. This is just a basic schematic outline of how the ME program works. Not really focusing on the left half of that flow chart, but more the right half. When we take information from the pavement structural response models, we're feeding them through damage models and transfer functions in order to predict what the distress or accumulation in IRI is going to be over time. And it's worth mentioning that there's two basic kinds of models going on here. There's one, the direct translation, which really only relates to basically one type of distress rutting. And that's where the pavement response is used to directly predict pavement distress. For the indirect translation, you have kind of an intermediate function with the damage model, accumulating damage and then relating that damage to the actual physical distress that's seen in the field. Now, for direct translation, give an example here. Pavement response, which is generated with the mechanistic model, either the simulated finite element model or the elastic layer program for flexible design. And that information goes through a transfer function and as it relates to observed distress. Specifically, if we're looking at rutting in an aggregate base, and this would apply to subgrade as well, the key response is vertical strain. And then the transfer function is basically plastic strain is going to be a function of that vertical strain. And rut depth in turn is a function of the plastic strain, basically your plastic strain times the thickness of your layers. So that's there's no you're taking that the pavement response and you're being able to translate that directly to the measured distress. But that's really only for rutting. It also applies to asphalt rutting as well. Now, most of the models entail some type of damage accumulation. So you're going from pavement response through the transfer function to the observed distress. And in this case, if we're looking at concrete cracking, mid-slab cracking from fatigue, the key pavement response is going to be the tensile stress at the edge of the middle of the slab. And the intermediate step in this case is going to be accumulating the damage over time from different loadings and different climatic situations. And then once the damage is fully accumulated for all the possible loadings that are going to go on through the design life, then the fatigue cracking is going to be a function of that damage accumulation. And the damage accumulation uses Miner's hypothesis or equation, where you have a maximum number of theoretical loads until you reach 100% damage, which doesn't necessarily mean 100% fatigue cracking, but we'll get into that a little bit later. And then your applied number of loads is going to be some portion of that allowable number, and you're accumulating that amount of damage for every possible configuration of loading within the design model. And just to give you a simple example, kind of how this works real quickly, if we have a paper clip and we go ahead and decide to bend it at different angles and try to figure out how many times we can bend it, return it to its original position, bend it again, return it before the end just snaps off, we can do that. And it's not going to be the exact same number every time, but we can accumulate enough tests, take the average of those, and then use that as the basis for the performance model. So in this case here, we are actually accumulating damage for different angles, or we're damaging the maximum theoretical amount of times you can bend the paper clip in each case. And as you would expect, when you're going from a low angle, 45 degrees, to higher angle, to 90 degrees, and finally to 110, you would expect the number of repetitions to decrease, and that is the case of what's happening. Now, if we wanted to do some combination of these different angles, we could do that. And as an example, in the table below, you see we're doing 20 repetitions at 45 degrees. Take that as a ratio of the average total number of repetitions, which is about 151, and your accumulated damage is going to be 0.133. And then you do that for 65 degrees, 90, 110, get each of those ratios, and then finally you get your total here at the end. So you're using an estimated 0.7 or almost 78.4% of the total damage life of that paper clip. So it's a very simplistic example, but in a way, this is really how we're applying it to the pavement design models as well. And to show you on a curve what's happening here is on a semi-log scale, looking at fatigue damage versus a percent slabs cracked. The basis for where it's 1 or 100% fatigue damage, as I said before, it doesn't relate to 100% cracking. It's actually 50% of the cracking. So you can exceed 100% damage when you're doing the analysis, and in some cases when you actually measure field performance, you will have you'll have more damage or more visual distress than 100% damage accumulation. And this is basically showing you how the typical increase in fatigue or in distress, physical distress, increases in terms of fatigue damage. Okay, now getting into the CAD itself, and what I'll do is I'm interspersing screenshots of the CAD. I'm not going through every screenshot of the CAD, but I'm going to integrate those into the presentation as you would step through it as the user, and then try to explain what's going on. So the first screen is going to be the logon screen, and just as a reminder, the CAT, the Calibration Assistance Tool, is available for anyone that has a regular Pavement ME Design license. And this is a web application. Okay, so, and this is the main user screen. The first thing that's going to be done is you want to start a new calibration. you select that. And first screenshot's going to ask for a name, project name, enter that, and then which pavement MED design projects are going to be used in the analysis. You have a choice of LTPP projects or owned projects. I'll explain a little more about what's available for LTPP, but if you select that, those files are already built into the CAT, so you don't actually have to upload those. If you prefer to upload owned projects, from your pavement management system, those you would have to load separately. And then the third entry is going to be selecting whether or not using standard US units or metric. And then finally, you're going to select which pavement MED design file version. So the CAT can analyze files from the desktop 2.55 or 2.6 version, as well as the web application, the 3.0 version. But you have to select which one it's going to be. So if you wind up uploading files that are a different version from what you selected here, it will not run the analysis. So the version of the files you upload has to match the file version that you're selecting here at this interface. And then you're complete and can start the calibration. You go back to the main screen. The next step is going to be uploading the ME design projects. So there are two types of files that the CAT needs to run the analysis. The first kind, as we mentioned, are the actual pavement ME design files, the ones with the DGPX file format suffix. And the second I say performance files, it's really singular because you're going to put all of your data in one file. It's going to be a CSV or comma separated value file format. And we'll show you the format in a minute here. But first, I mentioned the fact that the LTPP sections there are some that are already loaded into the CAT, so you don't have to do that yourself. But the ones that are available are the ones that were used for the global calibration. Now, most of those, which basically means most of the US test sections, there weren't as many of the Canadian LTPP sections. There are a handful, but the ones that aren't there would have to be created probably from the InfoPave data set. And this is just showing what model or what LTPP files are available in the CAT. And they match up with the calibration status. So in other words, for version 2.5 onward through 2.6 and 3.0, the last major global calibration for the flexible design models, and also includes the semi-rigid, was for the 2.5, 2.55 version. So those are all there. So they have everything across the board except the top-down cracking model was not yet incorporated in 2.55, but it was available for 2.6, the top-down fatigue cracking model. And then for concrete, since the concrete models, both jointed plank concrete and continuously reinforced concrete, were globally calibrated for the most recent version, the web application 3.0 version, because, well, two things went on there. We started using the Merit 2 climate data set for concrete designs, as well as the slab interface friction modeling from the NCHRP 151 project was incorporated. So because of those changes, the rigid models were globally recalibrated. So the LTPP files that were used for that would be available only for the 3.0 version. Okay, and this is basically how you're doing it. This is the screen interface for uploading the pavement MED design files. Make sure that you've run these files in the pavement MED design before you try loading them into the CAT, because you cannot edit pavement ME design files in the CAD. If there's a problem with them, you're not going to fix them there. So, and anytime you re-upload the same file, it's going to overwrite the existing file with the same name. And for the performance file upload, there's a couple links here that give you the data description for for each type of distress. There's a template provided, both one that's empty and with the sample data. Very important that the section ID must exactly match the pavement ME design file name so that the CAT can link them together doing the analysis when they run those. And the units, very important. I'm going to make sure that the units put in the performance file are of the correct format and match the prediction or the units that the pavement ME design program generates. So the user, again, as I said before, the user is going to be heavily engaged during this process. So if there's an issue with the performance data, the user is going to have to fix those. And this is just showing where the links are for the measured data description and the CSV file examples. And so this is the measured data description. This is the document that opens if you click on that. And it's just showing you what units to use for both US and metric. And here's an example of the CSV file for performance data. Don't get creative and rearrange columns or anything. Use it in this exact order. Obviously, the order of the performance state itself doesn't matter, but you want to make sure that the associated distress or IRI for each project entry matches it correctly with the column. And after that's done, after that's uploaded, you'll see a screenshot of the available project file names. Now, if there's an issue, if you uploaded a performance file that actually doesn't have performance data for one of the pavement ME design files, then it'll show it as being empty. If there is data there, then it'll show available. So these can be used for analysis when they're selected. So as far as the assumptions here, you should know which models, you should know which pavement types you're looking at, which models you want to verify or calibrate. You've already selected the test sections. You understand the importance, especially on the materials side. You want to calibrate or verify and calibrate using the same input levels as you would for a normal design. So that way you're going to calibrate the models for the conditions that you actually design pavements in as closely as possible. And as I mentioned before, the fact that you do want the performance data to be in the correct units, so that will have to have been done before the analysis, the CAD analysis begins, and confirm the overall data quality. So we're going to get into the performance models. And as I do this, I'm really skimming over the top. I'm not going to do a deep dive into the models themselves. That's really a whole nother webinar or another discussion. I would highly recommend, if you do want to learn more about how the performance models are built, to read up on them in the AASHTOWare Manual of Practice. And if you want to take a deeper dive than that, you can also look at the appendices that were used to generate the manual practice. And these appendices were from the original NCHRP 137A project. They are available at the AASHTOWare Pavement ME, pavementmedesign.org. No, .org website that Ben mentioned at the beginning of the webinar. So if you go there, you go into, I think, the software documentation under there. There's a link for the manual practice and the associated appendices, but that's where you'll get much more detailed information. My purpose here is to just basically identify, point out which calibration coefficients you have the ability to adjust and where they are within the damage models and the transfer functions. Anyway, so this is a screenshot. This is where you first select the actual performance models you're going to be looking at. You have to select which, so after you've uploaded the pavement image design projects, this is where you actually select them. So you can click on the drop-down list and select which projects you want to use. And then you're going to have to select the design type. So for flexible, under that category, you have basically new flexible, new semi-rigid, AC rehab. And then under the rigid category, you've got new jointed plane, new continuously reinforced concrete, jointed plane rehab, continuously reinforced rehab, and short jointed plane, but like there's actually no, you can't actually run this in the CAT. So it's listed here, but the performance model isn't available to calibrate for this yet, but something we'll add in the future. And then once then you have your list under each of these categories. In this case, this would be the listing for new flexible pavements. So you have the 5 performance models, and you're selecting whichever ones that you want to do the verification and calibration for. So for the flexible performance models, you can look at rutting, total rutting, and AC rutting, bottom-up fatigue cracking, top-down fatigue cracking, transverse thermal cracking, reflective cracking and overlays, and IRI. And this is a screenshot. It's kind of jumping ahead, but it's just to show you what the actual calibration coefficients are that can be adjusted within the CAT. And the calibration coefficient is listed here, the names, and then the actual global values that are currently used in these models. And we'll go over this a little bit towards the end of the webinar and what we're actually doing with optimization. So for the first one, asphalt rut depth, there's 3 coefficients that can be adjusted. I'll point out too the fact that you have the K coefficients as well, but these are really lab derived. So these initially are done in the current global coefficients are ones that were used for the global calibration, or the testing that was done for the global calibration. So these really don't get changed unless you're doing the testing yourself or your agency is doing the testing and can verify the new lab coefficients. Really what you want to look at are the beta coefficients as we're relating the distress model directly to measure distress. And then similarly for base and subgrade, you're going to have a beta coefficient for each of those. So the total of those 5 coefficients are the ones that are going to be adjusted within the CAT. And the table here just displays how the coefficients have changed, if they have changed at all, between the 3 versions in the CAT, 2.55 through 2.6 through Web 3.0. Now, as I mentioned before, the major global calibration occurred with 2.55, the last flexible one. So the coefficients have not changed through these 3 versions. They're still the same. For bottom-up fatigue cracking, this again is the list of coefficients within the optimization routine that are available in the CAT. And specifically, you have a beta F1, which is kind of called the intercept. If everything else goes to unity, then this is going to be the basically the intercept on the y-axis for the number of possible load repetitions. And then this is the tensile strain beta F2 coefficient. And finally, the dynamic modulus, the asphalt dynamic modulus beta F3 coefficient. So that's to calculate N, which goes into the damage index. And then the damage index goes into the actual fatigue cracking transfer function. So then you also have a C1, C2, C3 coefficient within the transfer function. Generally, you'll have a damage model. I'll back up here. You'll have the damage model and you'll have the transfer function. You generally start your calibration with the transfer function coefficients. You can back up here and adjust these as well, but you start, normally you would start with the transfer function, see if you can eliminate bias, and then hopefully improve the standard error, reduce the standard error. And as I did for writing, I'll show you what the current coefficient or what the current coefficients are for each of the three pavement design versions. And again, as same thing for rutting. The last global calibration for flexible pavement occurred with 2.55. And so the coefficients are the same through all three versions. Top-down fatigue cracking, there's two coefficients. There's actually three, but C3 is not yet available within the CAT. So that was actually a bit of an oversight, but that's another improvement that will be made in the future. Anyway, so this is for the amount of cracking as a function of basically the total possible fatigue cracking, adjusting those coefficients. And there's a difference here between 2.55 and 2.6. So 2.55 was still using the more empirically derived top-down cracking model. It was the new top-down cracking model is included for 2.6. So 2.6 and 3.0 have the same global coefficients. For thermal cracking, this is a little different from all the other models. For thermal cracking, there was actually a global calibration at each of the three different materials input levels, which was unusual because none of the other models had that done. Another thing was that through the global calibration for thermal cracking, it was discovered that there was something happening where above or below a certain temperature, below a certain mean average annual temperature, the MAAT, you could fully explain the cracking that was occurring from a cold thermal event. Above the temperature, which happened to be 57 degrees Fahrenheit, there was something else that happened. Not all the cracking could be explained that was occurring, and we suspect this is from shrinkage cracking in the asphalt that's not really directly modeled yet. So that's why the model was divided between those two temperature ranges for the calibration. So you have that happening for each of the three input levels. So there's actually 6 different possible global values for each of those 6 cases. Or I mean, 6 different scenarios that you're looking at. And this kind of explains what's happening here as far as how the model is subdivided by temperature above and below 57 degrees. It's going into the KT coefficient. The beta coefficient out here, this is what can be adjusted by the user. And right now it's just set at 0. So any adjustment, will basically add something to that or subtract something from the transfer function equations. And also to the fact that since it was calibrated at different input levels, globally calibrated at different input levels, there's also the associated standard deviation. We'll talk a little bit more about that later, but the standard deviation is basically the variance of the residual errors from the predicted values from the measured values. And the standard deviation is used within the pavement design to determine the impact of the reliability level that the user selects. Fatigue reflection cracking. Now, there's a fatigue reflection cracking model associated for fatigue for both full depth asphalt or for the flexible design and for semi-rigid. And there's 5 coefficients, C1 through C5. So you have 5 associated with new flexible pavement, and you have 5 as the same 5 associated with semi-rigid pavement. That's for fatigue cracking or reflection cracking from fatigue, which of course is going to be in the longitudinal direction. Then there's the transverse reflection cracking model coefficients. There's 4 of those associated with each case. And here you're going to have 5 different situations. 1, 2, 3, 4, actually 4, sorry, 4 different situations. So transverse reflection cracking will apply to asphalt and semi-rigid as well as the concrete designs, because concrete has cracks and joints. Those are going to reflect through. So you see the 4 coefficients here associated, C1 through C4 for transverse cracking. Transverse cracking in AC, and then the 4 associated with transverse cracking semi-rigid, 4 associated with jointed plane, and 4 associated with continuously reinforced concrete pavement. And with reflective cracking, the accumulated damage is basically going to be a combination of load-associated damage, temperature-associated damage. And breaking that down a little further, this is using fracture mechanics, which is used for the reflection cracking as well as top-down cracking models and thermal cracking models. You have a stress intensity factor, you have coefficients related to the mixture, the characteristics of the mixture, and then you have the C1, C2, C3 calibration coefficients associated with each one. So you have KB is going to be the bending, KS is going to be shear related, KT is going to be temperature related. So as it works out for fatigue cracking, bending and shear are going to be the predominant contributors to reflective cracking. For transverse cracking, the thermal aspect is going to be the main contributor to reflective cracking. And then once the damage is accumulated, that's plugged into the transfer function. And you have a C4, you do have a C5 coefficient as well. Again, similar to the previous model I mentioned. That's not currently in the CAT, but it will be added in the future. So C5 is available for it's available for longitudinal cracking. It's not available for, wait a minute, make sure I got that straight. Yeah, it can be calibrated. Yeah, okay. That's why I have it highlighted in red. C5 this is the global coefficient. However, you can't actually adjust that in the CAT right now, but you will in the future. So the C1 through C4 coefficients can be adjusted for transverse cracking, transverse reflective cracking. For IRI, these are the current global coefficients, from the screenshot in the CAT. And this is the actual transfer function itself. So it's a combination of your initial IRI, building off of that. And then there's 4 contributors for asphalt roughness. It's going to be the rut depth, fatigue cracking, thermal cracking, and then something called the site factor, which is basically the environmental element of this. Normally, if you're doing calibration, if you want to adjust something first, it's normally going to be the site factor to look at. And similar to the other flexible models because it was globally calibrated with the 2.55 version. Hasn't been done since. Those coefficients are going to be the same for all three versions. For concrete, for jointed plane, we can look at transverse fatigue cracking, joint faulting, IRI. And for CRCP, we're looking at punch outs as the primary distress and IRI. For short jointed plane concrete, longitudinal cracking, but as I mentioned before, that's not currently modeled in the CAT. So here's the current global calibration coefficients. For fatigue cracking, you have a C1 through C5, or C1, C2, C4, C5. There's no C3 coefficient. And you have both the damage accumulation model, and the main response here is going to be the ratio of the modulus of rupture to the actual tensile stress, or kind of what's I think it's called the critical stress function. You have the C1 and C2 coefficients for the damage accumulation. And then the damage goes into, the accumulated damage goes into the actual transfer function as it relates to the measured cracking distress that's seen. And for that, you have a C4 and C5 coefficient. As I mentioned before, as you're going through an optimization of coefficients, generally always start with the transfer function, and then possibly you can work back and look at decreasing the coefficients for the damage accumulation model. And the current coefficients, as I mentioned, there was a global calibration with the 3.0 version. It did not adjust the damage coefficients. And this kind of goes along with what I mentioned first. If you do an optimization, start with the transfer function. And that's what happened with the global calibration. It was actually the two transfer function coefficients, C4 and C5, that were adjusted from their previous values for the desktop versions. And this is basically what dialed in the performance model with the 3.0 version with the new global calibration. And here's the screenshot of the coefficients for faulting. There's actually 8 coefficients. It's a little confusing, so I'm not gonna get into the weeds on this too much. But you have a maximum mean faulting for a given month. And within that, there's going to be the C5, C6, C7 coefficient function which includes of different things, but includes the subgrade differential density of energy, which goes into or is derivative of a model that includes damage to the dowel. And that equation actually has the C8 coefficient. And then there's the maximum faulting, initial maximum faulting, which includes C5 and C6 again. And then has a C12, which is a composite of the C1 and C2 coefficients. And it's not all. There's actually there's the measured faulting, which has C3-4, which is a composite of C3 and C4 as a function of the heck was that far? It's an environment, it's something frozen something. Anyway, the point is you have 8 coefficients to look at. And with the global calibration that occurred, 1, 2, 4 of those 8 coefficients were adjusted. The other 4 remained the same from the desktop versions. For IRI, similar to the asphalt model, in this case, you have 4 coefficients, And the structure of the IR models looks very similar to asphalt. So it's going to be a composite of the effect of the distresses and a site factor. So you have transverse cracking, you have spalling, which is, it's a little unusual because spalling is it's a predicted distress, but it's not a direct output of the pavement ME design program. It's only used internally in computing IRI for jointed plain concrete pavement, and faulting, which is another predicted measure. So you have those three, and then you have the site factor, which again, this is very environmentally driven. And with the global calibration for 3.0, all four of those coefficients had to be adjusted from their previous values. CRCP punch-outs, 5 coefficients. Again, similar to jointed plane, you have kind of a critical stress ratio, modulus of rupture over the tensile stress. You have a C1 and C2 coefficient. So these are the coefficients going into the damage model. And then, or you punch out damage, PD, which then goes into the transfer function. And here you also have a C3, C4, and C5 coefficient to adjust. And from the global calibration with 3.0, again, the damage coefficients were not touched, but it was just the transfer function coefficients that were adjusted from their previous values. And finally, for CRCP IRI model coefficients, as you might guess, there's only one distress predicted, so there's only one that's going to be in the IRI prediction. So your initial IRI plus the contribution from punch-outs and the contribution from the site factor. And so you just have a C1 and a C2 coefficient. And these actually were not adjusted. So with the even with the globally calibrated models for IRI, these remain the same from the desktop version. Okay, so we've kind of run through the performance models. Now we'll talk about looking at the actual performance data and looking at the experimental matrix. So first of all, you have to determine how many sections you want to use for the initial verification and calibration. There's a formula. This is a screenshot, and it shows that the minimum number of pavement sections is going to be a function of what's called the Z value, which is basically, and this assumes a normal distribution, you know, the standard bell curve. This is basically the number of standard deviations from the mean. It's recommended to use 90% of the CAT, and that's going to be the default value used that you see in the next screen or two. And then the standard deviation of the maximum observed distress for all sections. So you would like the maximum of distress to be the last measurement, the most recent measurement. For a pavement section. Doesn't always work that way though, but whatever the maximum is, whether it's the last one or the previous or the one before that, that's the value that's being picked. And it's going to run a standard deviation it's going to assume the standard deviation. You're entering that for those sections. And then a tolerable bias, what your error can be, measured error can be. And there's basically a table that you can enter this in and generate the number of sections. So this is showing you the default for both asphalt and concrete. And again, this is assuming a Z-variate for 90%. And the tolerable bias for each of the distresses for AC and for jointed plain concrete is listed here. And then the recommended standard deviation of the maximum observed distress is also listed here. You can change these if you want to. If you change these, then the number of sections will also change. But this is the recommended number that you should have. And the reason why this is important is when you're running the CAT, if if you do optimization, if you make it through verification and decide you want to optimize the coefficients, and if you would like to do normal split sampling. So in other words, you're going to have part of the data is going to be used for the actual optimization or calibration. And then you're going to have an independent set left over to validate or you check the accuracy of your calibrated model. And the normal split is going to be 80-20. So 80% will be used for the calibration optimization, 20% will be used for validation. If you don't have the minimum number of sections, the CAT will automatically lump all of those sections into the optimization. So 100% of the sections will be used for optimizing the coefficients. You will not have an independent set left over to do the validation. Now, what are we looking for? Just general guidance for the pavement test sections that are input in the CAT. You would like to see generally somewhere between 15 and 25 years as the average life. For rehabilitated pavements, mostly overlays, somewhere 10 to 15 years is good. Now, if it's ideal to have some older pavements in there because you can have durability related distresses which aren't modeled. So in other words, it's kind of including it as a fudge factor in the calibration. You can't directly model, for instance, decracking in concrete or stripping in asphalt, but you are taking that into account, measuring performance of older pavements. So you're going to have normal, fatigue-related distress, but then you'll have some contribution from these other factors that you're not directly modeling. But by incorporating that in there, you're basically baking that into the new calibration of the models. And this is a screenshot showing you the bar chart for the ages or the age distribution of the sections for this particular example. And here you can see on the right side, the table shows that the mean age is almost 18 years, which is, within the range we're looking for new pavements. That's good. And then it's going to show you the average maximum distress values. So ideally, you want it to exceed 50% of the design threshold. So as an example, let's say we're using a 1/2 inch for total rutting as our distress threshold. So 50% of a 1/2 inch would be a 1/4 inch. So in other words, the average of the maximum rut measurements that we have from all the sections ideally should be at least a 1/4 inch. And this gives you an opportunity to identify any anomalies, major outliers. And then you can reconfigure the final matrix based on the analysis of performance data. In other words, you may throw out data and then include some other sections. And this is showing a bar chart screenshot for the maximum distress. This case here, our mean, I think this would be fatigue cracking. So 3.83%. I'm guessing the threshold, who knows, might be like 10 or something like that. So in that case, you're not really meeting the minimum 50% criteria, and that's going to happen a lot. So you may not meet the minimum for the distress threshold. You may not meet the minimum for the average age. So what do you do in that case? I would still recommend going through with the verification and the calibration. You have to have a starting point somewhere. So what that basically means is that you could have a bias for older pavements that you have not yet discovered simply because you don't have the performance data to verify whether or not there's going to be a bias. But the first calibration you go through is always going to be the hardest. It's the legwork doing the test section selection, going out there, collecting data, scrubbing the data to match the pavement ME design outputs, doing a lot of materials testing, all that stuff up front. Once you do it initially, you're not going to have to do that again. Mostly what you're doing is just adding more performance data and including that in future calibrations. So even if you're not fully fleshing out the long-term performance of your performance models, I would still strongly advise, get started. Don't delay, and at least have that starting point, and it's going to be much easier to go through this in the future. So prior to uploading data, and we've kind of touched on this already, you should check history plots. The CAT's not going to do that for you. It's not going to generate those history plots. You need to do that for each specific pavement section that you're running through the CAT, and then you remove anomalies that can be explained as measurement errors, maintenance activities, or any other justifiable reason, and then leave in anything that may look a little funny but still within your normal measurement tolerance. Here's an example. So this is transverse cracking. So let's take a look at this. This is going from 1992 through 1998. So we start at 571 feet. We go down to 443 the next year. This could be a reasonable measurement error. Then in the next year or 2 years later, you're jumping up to 1800. Possibly you could have had some extreme cold weather event to initiate that. So yeah, this might still be good. But then a year later, you're dropping down, or less than a year later, you're dropping down to 1100 feet. So this looks a little funny, and it's staying about the same the next year. So these data points probably need looking into. And then all of a sudden, you're soaring up to almost 2400 feet. Now, if you'd gone directly from 1800, 1880 to this, that would kind of make sense as it increases. So these are questionable. But look what happens here, going from 97 to 98. You're dropping off from almost 2,400 feet to nearly nothing. Obviously, if these are both accurate measurements, then obviously something happened here. More than likely, the road got resurfaced and your transverse cracks disappeared at least for a year. That's something you have to look at. So this requires some effort, some analysis. You don't want to just indiscriminately include all this data, because it's really going to could affect the bias, will definitely affect the standard error of the estimate, or the standard deviation of the residual errors. And here's a screenshot showing what the matrix looks like. It breaks it down into these different categories. So here you have subgrade type. This is what the CAT can do, okay? So keep that in mind. You could further granulize these sections by different other subcategories that you can think of, specific material characteristics, something else, but you have to do that on your own. Right now, this is what the CAT is capable of. So you can break it out by subgrade, coarse grained, fine grained low PI, fine grained high PI. You could break it out by the mean average annual temperature above or below 57 degrees. Break it out by annual precip, less than or greater than 20 inches. And then the structural thickness, you can actually adjust these ranges here. So you have three different thickness ranges for the pavement, flexible pavement in this case, and then also 3 different traffic levels you can do. So do you have to have sections in each one of these cells? No, you don't. It looks good as far as balancing it goes, but you want the cells to represent the actual conditions that you construct your pavements in. So if you're missing sections from something that you think is prevalent in your state, then I would look at trying to acquire more test sections. If you're happy, even though there's not a lot of cells filled here, but these are the ones that are representative of the construction characteristics within your agency's jurisdiction, then go with those. As I mentioned, you are restricted to what you see here. And then similarly for the concrete models, these are the breakdowns. You have the same subgrade, mean average annual temperature, precip, and thickness and traffic. Now, verification. So let's assume we've reached the point to where we've uploaded all our files. We've already critiqued the data. We've thrown out outliers, and we're happy with the matrix, how the matrix looks. So we want to go ahead and initiate the verification. So first thing that has to be done is you have to associate the coefficients, the model coefficients, the ones that you want with your Pavement ME design files. And so here you're going to select either the global model coefficients, which are basically kind of the default coefficients, or you're going to import local calibration coefficients that you've already used from, say, previous local calibrations. Could be a second one that you're running. And then you click update. And so that's a fairly quick process. You proceed, and then you have your list of all the files, and then you run the files. This will take a little time. So in this case here, I think we've got, I don't know if we had the number here, so not sure. I think we might have had like 70 files here. Anyway, it's basically running each Pavement ME design file. So think of how long it takes to run the Pavement ME design program. So if you got 60 or 70 files, it could take you, between an hour or 2 hours, assuming you're not in queue behind somebody else. But as long as that's not the case, that won't take an inordinate amount of time. But just have to be aware that it's not gonna update everything automatically. Run that, and then after you do that, you get basically the graphical and table views of the data. Now, you're going to have a tab for each model that you're doing the verification for, and you'll be able to select each one individually. In this case here, this is showing bottom-up fatigue cracking. So you select the model to view. You'll have the graph of predicted fatigue cracking, bottom-up fatigue cracking versus measured fatigue cracking. And a nice feature is, I can't show you how it looks, but if you hover your cursor over a data point, it'll show all the data points. It'll highlight or expand all the data points associated with that particular test section. So the reason that's good is if you're trying to, at the initial verification, if you're looking at outliers or anomalies, you could identify that there's a section or two that's kind of driving the data or basically increasing the standard error and affecting the bias. And so you would then have the opportunity to deselect those sections and rerun the statistics. Meanwhile, here on the side, you can see the bias. So you have minus 3.7% fatigue cracking is the bias, which makes sense because you see most of the data is below the line of equality. And then the standard error of the estimate. Again, SEE is basically the standard deviation of the residual errors of predicted minus measured data. And you have R squared. You have a few other statistics for the intercept and the slope. And then you have the 3 null hypothesis values, which is basically for the slope equal to 1, the intercept equals 0, and the difference between predicted and measured equals 0. And we'll talk a little bit about what, in a couple minutes, we'll talk about what the recommendations would be for some of these statistics. Anyway, on the side here, you have the opportunity to filter out certain types of sections. And again, you're limited to what you see here. So you can do it by binder type between neat or polymer modified. You could do it by thickness. So you have 3 different ranges in this case to match what you have in the matrix. In this case, it's less than or equal to 5 inches, between 5 and 10 inches, and then greater than 10 inches. So if you say deselect all the sections less than or equal to 5 inches, those points will disappear from the graph. It'll recalculate the statistics. And so you can see here whether or not taking out certain categories of the sections will improve your model fit statistics. So that's basically what you're doing here in the verification process. And then update that, deselect or select and update it. And then this is all, the graph will change, and the table here will adjust as well. So just kind of statistics 101 here a little bit. What are we trying to do? Okay, so we have 2 things we're trying to improve. We want to try to reduce both the bias and the standard error as much as possible. Here's a case of where you see the line of equality. Ideally, we'd like all our points to be clustered closely on this line here. But in this case, it's not happening. So we have a bias. We have a kind of a consistent error from the line of quality. But for the modeling of that new trend, you still have, there's very low standard error. There's little difference between, if you're using this as your new model, there's little standard deviation of the residual error between predicted and measured data. So that's a high bias, low standard error case. The opposite is, they average, on average, their performance instances do average such that the predicted distress does equal measured distress. The problem is you have a pretty wide, high standard deviation of the residual errors. So that's not good either. And then ideally, this is what we want. We want low bias. The trend is the line of equality, and we have pretty tight spacing here, so we have low standard error. So when you're looking at a verification graph, you want to see if you can identify groups of data or groups of test sections that are driving or increasing either the bias error and or the standard, or the bias and or the standard error. In this case here, you can kind of see there's three categories that have been identified. So you have to ask some questions here. First of all, why are these groups? What common materials feature or environmental feature? What is common about these groups? Are there structural differences? That you can identify thicker from thinner sections by doing this? Are they in different environmental regions? Did they have some type of material-related defect that was known, at the time of construction, perhaps? And finally, should they be excluded from the matrix? So you can exclude the data, and you can improve the data. But the problem is you're narrowing the applicability of the model to your performance sections. So if you take these sections out, you have to decide, how are you going to model these particular types in the future? So you could do the local calibration for the reduced data set, and then maybe try to do a local calibration for these smaller data sets. You could just set them aside as, say, just resolve to try analyzing later, or perhaps you're aware you may not be constructing these types of pavements in the future, whatever. I mean, you have some decisions to make here, but you just have to realize is that once you start dividing these into subgroups, then you really have to be treating them differently analytically. And so here's a case of, on average, it looks like the bias is I don't know exactly, but it looks like it's close to 0. Obviously, there's a higher standard error with this data, predicted versus measured. So breaking it out, you find out that by thickness, it's actually under predicting for thicker pavements, which could be rutting probably, let's say under predicting rutting, in this case for thicker pavements. And for thinner pavements, it's actually over predicting it as it compares to measured data. So again, do we analyze these differences? So if we were to just use this data set, we could probably reduce the bias pretty easily and then have a relatively low residual standard deviation of the residual error. And similarly, we could also calibrate, optimize this grouping of the thicker pavements and come up with, so both these cases, we can reduce the standard error, but again, we're going to have to model these individually. We're going to have a different set of coefficients for the thicker versus thinner pavements. So you can stay with this. You can have, I think this would be a pretty low bias, but again, you would have a high standard error. So what can you live with? General guidance for looking at these statistics. And this is kind of the basis that we use internally when we're looking at verification and calibration of performance models, is it shows you the range for the R-squared as it relates from very good to poor. And then there's a recommended standard error of estimate, or again, the standard deviation of the residual errors range from good to poor for rutting, for fatigue cracking, transverse cracking, RI. This is for, of course, flexible models. And then for the hypothesis testing. Now, with the hypothesis testing, you want the p-value to be over 0.05, above that 5% significance level. If it's above it, then it's not that we're not saying it's true. We're saying that we fail to reject it. So in other words, we don't have enough evidence to say that it doesn't work, so therefore we assume it does work, is basically how, what we're doing here. And if it's below 0.05, then it's rejected. And then on the concrete side, again, you have recommendations, same recommendations basically for R-squared, and then different ranges for the transverse cracking, joint faulting, and IRI models, and the same criteria for the hypothesis testing of the 3 for slope, intercept, and difference between predicted and measured data. So in summary, the user is looking at the data, deciding whether or not the statistics are acceptable, looking at filters to improve the statistics, and then finally just coming up with what the final matrix structure is going to be if you want to go forward with the optimization of the calibration coefficients. And it is, as you noticed, an iterative process. So you can go through that multiple times. And what the CAD is doing for you, it's doing again, the heavy lifting. It's populating all the data tables, plots, calculating the ANOVA statistics, and populating those results for you to look at. And then if you filter the data, it updates all the figures and tables. So it's doing, all the analysis for you. So the verification process. So what happens if we look at the verification and the bias and the standard deviation of the residual errors, in our opinion, is acceptable? Well, we're good to go. If those are the global calibrations, then the global calibration coefficients are still reasonable to use for your particular agency's performance models. if you're not happy with the results, then you go on to the calibration optimization. So we do that. We proceed from the verification. So now there's a kind of an artifact in the coding where you actually have to go through, try to explain this, probably something we'll try to improve in the future. If you have enough test sections to do the normal 80-20 split that I talked about earlier, splitting it between calibration and calibration validation, you have to select each one of these tabs individually and go through the C. Select it, click on it, update the project list, and that'll push you forward into the optimization screen. Then you have to back up and do this over again and click total running. If you're going to do all four of these models, click total running, update project list. It puts you into the optimization screen. You back up, do transverse thermal cracking, update project list, back up, and then do IRI. That way, after you do the optimization of the calibration coefficients, it will leave the 20% set aside for the independent validation of the models. Okay. Now there is a sequence, a recommended sequence, and this is logical. You want to do the distress-related models first. And then once you do those, you take those, if you wind up adjusting any of the coefficients, you reincorporate those into the models. And then if you're going to do an overlay, rehabilitation, then you use these once you get that, if you think about it, all these are going to be contributing factors to IRI. So you want to theoretically dial in the models as best as possible before you do the calibration for IRI. And similarly, on the concrete side, you want to do the stresses, transverse cracking, faulting on JPCP. Punch outs, recalibrated coefficients, plug them into the models, into the files, and then you're doing the overlay calibration, adjusting those coefficients. Then you take those coefficients, plug them back in, and then you do the International Roughness Index. And obviously, if you're not doing an overlay, you just skip the step here, go right from the stresses, use those to calibrate the IRI model. So what you'll see is, and this is, I kind of showed you the screens earlier when I was just identifying or showing you what the global values were. You're going to select, and I should have had a better screenshot here to show you. You're actually selecting new value, and then you put a minimum value and a maximum value in the increments. And I want to point out that the number of increments, this isn't the same as pavement MED design. The increment is going to count as a beginning and starting point. So if I have 3 increments, I say 0.53 to 0.57. The first increment is going to be 0.53. The second is going to be 0.55 in between, and then the third will be 0.57. Unlike the pavement MED design, which 3 increments means there's 2 measurements in between here. So it'd be like, increments plus 1 in the case of pavement MED design. But for the CAT, this includes, the increment includes the starting and the ending point. And then run, and then wait. Possibly a long time. We'll get into that a little bit in a few slides. But here's the results. When your optimization is finished, it'll show you the set. In this case here, we had 1 coefficient that we had 7 increments for. So we're getting 7 results. And this is showing the yellow dashed line is the standard error. The blue dashed line is bias. And you can see as I assume, it was increasing the coefficient. we kept improving the statistics. You select the one that's best and then accept it, and then it changes the coefficients and lists those as the replacement for the global coefficients. And then after you do this, it also shows you the graph for predicted versus measured, as well as the graph for residual error, predicted minus measured, and your ANOVA statistics here on the side. So as an example, the case of the beta 1R coefficient, beta R2, beta R3. So beta R1, which is the intercept coefficient, you can see how increasing the coefficient increases the rutting prediction, which makes sense if you look at where it's at within the equation. So increasing this number is obviously going to increase the cumulative rutting that occurs. And this gives you an idea of what's happening. Same thing for beta R2, increasing that coefficient also increases rutting. And then beta R3, the load repetition related coefficient also increases rutting as the coefficient is increased. And this is showing the one for the beta S1 for both any unbound layer, whether it's base or subgrade. Increasing this coefficient increases the predicted rutting. And this is showing for bottom of fatigue, you have the beta F1 and the beta I'm sorry, no, this is the C1. This isn't the transfer function. This is the C1 and C2 coefficients. And as C1 increases, let me make sure I got this straight. Let's see. Yeah, as C1 decreases or increases, then the fatigue cracking prediction decreases, which is how it's supposed to work. This one should work the same way, but I had an email from somebody a couple weeks ago, a user, actually it was a student, that said, "Are you sure this graph is right? It looks like it should be the opposite." And yeah, sure enough, good catch. So I probably should have deleted this graph here, but this is actually backwards. You should see the opposite effect with increasing the coefficient here for the C2 coefficient. And reflection cracking, showing the impact of the C4 coefficient and the C5 coefficient. And so there's a user guide for the CAT that's in the program, so you can open up and look at these graphs. These graphs are not all inclusive. We don't have every possibility. We will add more in the future. So these probably do need to be revised a little bit. And for cracking the C4 and the C5 coefficients, the impact of increasing those. And so in summary, you want to select the coefficients, select which coefficients to adjust based on the data. So the user's making the decision which coefficients to select, whether from the transfer function or perhaps the damage model, and have an idea of what the impact is. If you decrease it, what's it going to do? If you increase it, what's it going to do? Then run it, review the results, and determine if another iteration is needed, and quite often it will be. The automated process, real heavy lifting here. So it's sending these optimization sets and projects to the analysis server, running all the sets, and then letting you know when they're done and populating the statistics. Now, run times. How long does this take? And this is assuming you're not in queue. That's an issue we're dealing with. More and more people are starting to use the CAT. It's becoming popular. I know from personal experience, I can get hung up for a day or two waiting to run my calibration routines. And, we're going to open the server capacity in the future to accommodate more users. But anyway, the general rule of thumb, although this is with the refactoring and improvement of the design models that have occurred, these run times will keep getting shorter in the future. But this was just this is from several years ago, giving you a rough idea. You run the first. Okay, so it's running every design. So let's look at this. Say we have 5 coefficients we're adjusting at the same time. I wouldn't recommend that. And each coefficient has an increment of 5. So you could basically take the number of coefficients to the power of the different coefficients, 5 to the 5th power. And that's 3,125 possible combinations. You have to run each one of these for a single file. So if you have one file, that could take 26 hours. If you had 100 projects, 108 days. Again, don't do this. Here's a simpler case. So this is where you have only 2 increments, but again, you have 5 coefficients. So 2 to the 5th power is going to be 32, much more manageable for one project, a little over a half hour, 100 projects, a day and a half. And you can see what's going on here. Now, if you don't have, if you know, you don't have to do the same number of increments for each coefficient. So basically, let's say we're only doing a BR1, BR2, and BR3. We have 3 increments for BR1, 4 increments for BR2, and 5 increments for BR3. That would be 3 times 4 is 12, times 5 is 60. So doing that would be 60 combinations. And how long does each one, or how long would that take? The first run is always going to be the longest because you're going through a normal pavement ME design analysis. The next ones are shorter, much shorter, because it's not repeating some of the work. For instance, the EICM, the Enhanced Integrated Climatic Model, only runs once. And since that data is not going to change for the all the other project coefficient combinations, that doesn't have to be run again. Just basically only the executables within pavement ME design that are directly affected by the change in the calibration coefficients are being run. And so if you want to get a rough idea of, use this formula, but again, this has improved with time. So this is conservative at this point. But again, keep in mind, that's assuming you're able to run right away. And it's very likely you could be in queue behind somebody else. So that's an issue we're aware of and trying to deal with and improve. Finally, last step is the validation review. This is showing predicted versus measured. This is for that 20% of data that was left over. And this is showing the residual error graph. So you want to check that against the calibration coefficients and consider rerunning optimization if there's really, if the validation is that bad. But keep in mind, it may not be as good as the optimization set simply because you don't have a lot of data for the validation. And so any variance is going to be magnified with that lower number of readings. But if you're happy with it, then you're good to go. So, and then this is another screenshot that's generated. So this shows you side by side. You're looking at the initial verification, the optimization of the coefficients with the 80% of data, and then the validation with the remaining 20% of the data. And so you can compare the statistics side by side. And the last step is a standard deviation. So this is where you generate the standard deviation equation that's used in pavement ME design. And this is very important because based on what the standard deviation is, if you have, say, use a reliability level of 90%, that value at 90% is directly impacted by what this equation is. And the way you do it is you adjust the number of bins. So you can push this, put the button up or down, and it will evenly distribute the number of entries into each of these categories. And it's increasing with damage. So the first bin will be the lowest grouping of distresses. Second bin will be the second highest. And what you logically expect to see is you expect to see the standard deviation increase as the distress increases. And it won't always do that. It could bounce around a little bit, but Yeah, I don't have really concrete guidance other than to say that, you want the bins to have, a healthy number of sections each one. So you don't want to increase the bins too much to where you have a small scattering of data each one. Generally, if we're doing this, we're going to pick something between 6 and 8 bins usually. And so you'll have, depending which one you pick, you're going to have a different formula to use, which is shown here at the bottom. When you're happy with everything, all done, you've optimized your coefficients, accepted them, gone through the validation, looks good, and then you've generated your standard deviation formula, then you can export all that into an XML file down here, and that's what's used in the Pavement ME design program. Import it in there, and you can start using your new locally calibrated coefficients. And that is basically it. So I'll let you take over, Ben.
All right, thank you so much, John, for that presentation. I think we have a one last poll to launch. Let me get that going. And of course, thank you to the rest of the ARA team for putting that together, presenting and answering questions. There were a lot of questions that came through, a lot of really good questions. One open question though, I think someone might have just answered it. Just wanted to make sure. Somebody just asked, do we need a separate license for the Calibration Assistance Tool, or is it already included in the Pavement ME license? And that was answered, yes, it is included in Pavement ME license. As you guys take this poll, I would like to share a couple of things, a couple of announcements. One, in the chat, the registration for the user group this year is available. It's in the chat here. Got sent out via an email, but you can always go to the link I put in the chat as well. Again, as you're filling out this poll, a couple announcements. Again, the user group registration is open. And then secondly, at AASHTO, another technical service program called AASHTO Technical Training Solutions, which provide various training for different agencies, now includes a training session on mechanistic empirical pavement design. That can be found at AASHTO.org, going to the AASHTO store and searching through training. We just launched that training recently. It is free for contributing states to that program and available for consultants to purchase as well. If anybody has any questions about either the user group, technical training solutions, future webinars, anything like that, please shoot the questions to myself, John, anybody on the task force, or email pavementmedesign@ara.com. And thank you everyone for answering the poll questions. Looks like about everyone has participated in that. So I will go ahead and end the webinar and look forward to seeing everybody at the next one. The next newsletter will advertise any of the upcoming webinars, as well as that user group. Contact information for everyone. John, if you go back just one page, contact information for everyone is on this page. That includes everyone on the task force, leadership-wise, ARA staff, Ryan at AASHTO, and links to the website. So thank you, everybody. Appreciate it, and we'll see everyone next time.